Chapter 16 Interpretation. As we have seen, logistic regression models model the probability that a particular event will occur using a linear combination of predictor variables. In modeling, the parameters of the logistic regression model are optimized to best fit the observed data. The optimized model outputs the results of the analysis. In this chapter, we will see how to interpret these results. In the logistic regression model, a coefficient beta I is obtained for each predictor variable xi. These coefficients determine the strength and direction of the impact of each predictor variable on the logos, calculated by the probability of the outcome. The strength of the effect is the extent to which a one-unit change in the predictor variable causes change in the logos. The direction of influence indicates whether the logos increase or decrease when the predictor variable increases. An increase in logos represents an increase in the probability of an event occurring, while the decrease in logos represents a decrease in the probability of an event occurring. Let's take a closer look at how to read the values of the predictor variables. The strength of influence is expressed in terms of the absolute value of the coefficient of each predictor variable. The absolute value of the coefficient of a predictor variable represents the change in logos associated with the one-unit change in that predictor variable when the other predictors are held constant. The direction of influence is represented by the sign of the coefficient of each predictor variable. When the coefficient is positive, an increase in the predictor variable increases the logos. In other words, an increase in the predictor variable increases the probability of an event occurring. Conversely, when the coefficient is negative, the logos decrease with an increase in the predictor variable. In other words, when the coefficient is negative, the probability of an event occurring decreases with an increase in the predictor variable. For example, if the coefficient of predictor xi is 0.2, the logos increase by 0.2 when only predictor xi increases by 1, while the other predictor variables remain unchanged. Let's take the results of the analysis using Python's stats model as an example to see how to interpret the model. The dataset used was part of the breast cancer dataset provided by scikit-learn. When logistic regression analysis is performed using stats model, the first part of the output result looks like this. The current function value represents the value of the negative log likelihood function calculated based on the model fitted to the data. That is, it corresponds to the cross-entropy error. Since the cross-entropy error is a loss function of the logistic regression model, the smaller this current function value is, the more accurately the model represents the data. Iteration refers to the number of iterations performed by the optimization algorithm to maximize the log likelihood function, that is, minimize the cross-entropy error. The optimization process starts with initial values of the parameters and updates them based on the gradient or derivative of the objective function, gradually decreasing the value of the objective function. This process continues until a predetermined stopping condition is met. This condition is determined in advance by the analyst, such as the change in the value of the objective function falling below a certain threshold value or the maximum number of iterations. The value of iteration indicates the number of iterations until the model converges and represents the convergence speed or difficulty of the optimization process. If the number of iterations is very high, it may indicate that the optimization process is difficult or that the initial values are far from the optimal solution. On the other hand, if the number of iterations is low, it means that the optimization process is converging quickly. As a summary of the results, the following table is output. The title, Logistic Regression, is another name for a logistic regression. The lower portion provides information on the constant term and the coefficients and the statistical significance of each predictor variable. The coef is the coefficient of each predictor variable in the logistic regression model. This value indicates the magnitude of the effect that a 1 unit increase in that variable has on the logos of the objective variable. A positive coefficient means that the variable increases the probability of the objective variable, while a negative coefficient means that the variable decreases the probability of the objective variable. STDERR is the standard error of each coefficient. It indicates how reliable the coefficient estimates are. The smaller the standard error, the closer the coefficient estimate is to the true value. Z is the z-statistic of the coefficient. It indicates how far apart the estimated coefficients are in standard deviation units under the null hypothesis that the regression coefficient is 0. The z-value is computed by dividing the estimated value of the coefficient by its standard error. P is greater than absolute value of z is the p-value. The p-value is a value to evaluate whether the coefficient is statistically significantly different from 0. In general, a coefficient is considered statistically significant if the p-value is less than 0.05, indicating that the variable has a significant effect on the objective variable in the model. The number 0.025, 0.975 is the 95% confidence interval for the coefficient. This interval means that we are 95% confident that the true value of the coefficient is within this range. Next, let's look at the top left. Depth variable is the name of the dependent variable. Here, we name the dependent variable as target. If we had named the dependent variable something else, the name would have been printed. Model is the model used in the analysis. In this case, we use the logistic regression model, so it is labeled Logit. Method is the optimization used in the analysis. MLE is an abbreviation of maximum log likelihood estimation. Date and time are the date and time of the analysis. Converge indicates whether the optimization algorithm converged, that is, whether an optimal solution was found. Here, it is true, which means that the optimization was successful. Covariance type, non-robust, means that the default setting makes the following three assumptions in the analysis: independence of error terms, equal variance, and error terms follow a normal distribution. Independence of error terms means that the errors between observed and predicted values of the dependent variable do not affect each other across samples. Equivalence means that when the errors between the predicted and observed values for each sample are aggregated, their variance is uniform and has the same degree of variation regardless the value of the forecast or predictor variable. Error terms follow a normal distribution means that the error values are normally distributed, when the errors between the predicted and observed values for each sample are aggregated. When these assumptions are not met, it is possible that variables not included in the model have a strong influence on the dependent variable. It is also possible that the model does not adequately capture the structure of the data. That is, the data cannot be approximated by a logistic regression model. Next, let's look at the upper right part. Number of observations represent the total number of observations in the dataset. The value of df residuals is degree of freedom for residuals, which is the total number of observations minus the number of parameters included in the model. Why this is important will be explained later. df model represents the degree of freedom for the model, which is the number of parameters other than the intercept, or the number of coefficients included in the model. In other words, it equals the number of predictors included in the model. The value of pseudo R squared is equivalent to the R squared, or coefficient of determination in linear regression. This metric will be explained later. The value of log likelihood is the log likelihood value of the model and represents how well the model explains the data. In logistic regression, optimization is performed to maximize the log likelihood. Therefore, a higher value for the log likelihood indicates a better fit of the model. Since the likelihood function takes values between 0 and 1, its logarithm takes values between 0 and negative infinity. In other words, the log likelihood function never takes a value greater than 0. Therefore, the larger the value of the log likelihood, that is, the smaller the absolute value of the log likelihood, which is a negative value, the better the model explains the data. The value of LL null represents the log likelihood of the null model. By comparing this value to the log likelihood of the full model, we can evaluate how much information the predictors add to the model. The full model is the model that has been optimized by adding the predictors. That is, the model we have constructed for this analysis. The value of LL null can be better interpreted by looking at it in conjunction with the underlying LLR p-value. The LLR p-value is the p-value of the log likelihood ratio test, which evaluates the statistical significance of the difference in log likelihood between the null and full models. A smaller value means that the full model statistically significantly explains the data better than the null model. In the next video, I will explain some of the metrics in more detail.